Hey everyone! In today's video, we're going to explore the key components that make up the Kubernetes architecture. When learning Kubernetes, understanding each part of its architecture is the first step you need to take. By getting familiar with how these parts work together, you'll be able to use Kubernetes more effectively. If you've watched other videos on this channel, you'll notice I love to relate tech concepts with real-world scenarios. And today, we'll use a traffic system analogy to explain Kubernetes architecture in a clear and simple way. Whether you're new to Kubernetes or looking to deepen your knowledge, this video will give you a clear overview of its components and how they interact to manage applications. Without further delay, let's dive in. There are different ways you can create a Kubernetes cluster using tools like Minikube or kubeadm locally, or leveraging cloud services like Amazon EKS, Azure AKS, or Google Cloud GKE. But regardless of the method you choose, the basic setup remains the same, and it includes the master nodes, also known as the control plane, which manages the cluster, and the worker nodes, which run the application containers. Now let's look into these in more detail. The control plane acts just like a city's traffic control center by overseeing everything happening in the cluster, ensuring smooth operations. Now let's break down the main parts of the control plane. First, we have the API server. The API server is a central component of the Kubernetes control plane, responsible for handling all communications and commands within the cluster. It is the primary entry point for all administrative tasks and operations. The API server exposes the Kubernetes API, which is an interface that allows users and internal components to interact with the cluster. From a more technical standpoint, the API server performs several critical functions. First, it handles all requests which can come from various clients such as kubectl, the Kubernetes dashboard, or other custom tools. These requests can include operations like deploying new applications, scaling existing ones, checking the status of resources, or modifying configurations. The API server is also responsible for authentication and authorization. When a request is received, the API server verifies the identity of the user or component making the request by checking if the request is permitted based on predefined roles or permissions. This ensures that only authorized users and services can make changes to the cluster. Another key role of the API server is to act as the communication hub for all other control plane components. It interacts with the etcd database to store and retrieve the cluster state and configuration. For example, when a new pod is scheduled, the API server updates etcd with this information. It also communicates with the scheduler and controller manager, passing along necessary information and ensuring that tasks are executed correctly. I know the components I just mentioned might sound unfamiliar to some of you, but we'll get to them shortly. So in our city traffic analogy, think of the API server as the central traffic control center. It receives information from traffic sensors, aka requests in our case. It decides if the actions are allowed, that is, the authentication and authorization bit, and then sends instructions to traffic lights and road signals, which in this case are the control plane components to manage the flow of traffic. Next, we have the etcd database. The etcd database is a distributed key value store that serves as the primary data store for Kubernetes. It is responsible for storing all cluster state and configuration data, ensuring that the information is available to all control plane components. etcd is designed to be highly available and consistent, making it a critical part of the Kubernetes architecture. Technically, etcd stores the state of all Kubernetes objects such as pods, services, deployments, and many more. This includes both the desired states and the current state of these objects. So when changes are made to the cluster, such as adding a new pod or scaling a deployment, these changes are recorded in etcd. etcd achieves high availability by running as a cluster of nodes which ensures that the data is replicated across multiple instances. This replication allows etcd to continue functioning even if some nodes fail. One of the key features of etcd is its ability to support watch operations. Basically, what this means is it allows other components such as the API server to subscribe to changes in the cluster data. When a change occurs, etcd notifies the subscribers, enabling them to react accordingly. For example, if a new pod is scheduled, the API server updates etcd and the scheduler is notified to place the pod on an appropriate node. In our city traffic analogy, etcd acts as the city's central database, storing all information about traffic lights, road signs, and traffic conditions. When a new traffic light is installed or the timing of a light is changed, this information is updated in the central database, ensuring that the entire traffic management system has the latest information. Moving on, we have the scheduler. The Kubernetes scheduler is a critical component responsible for assigning pods to nodes within the cluster. Its primary function is to ensure that workloads are efficiently distributed across available resources, taking into account various constraints and policies. Technically, the scheduler performs several key tasks. When a new pod is created, the scheduler determines which node should run the pod based on its resource requirements and the current state of the cluster. This decision-making process involves evaluating factors such as CPU and memory availability, node affinity and anti-affinity rules, and any custom scheduling policies defined by the user. The scheduler is responsible for selecting the most suitable node for each pod. Once the scheduler selects a node, it updates the pod specification in etcd, and the kubelet on the chosen node is notified to start the pod. The scheduler continuously monitors the state of the cluster, ensuring that workloads are balanced and resources are utilized efficiently. The scheduler also supports advanced scheduling features such as taints and tolerations, which allow users to control pod placements more precisely. Taints are like labels which can be applied to nodes to indicate that they should not accept certain pods unless these pods have matching tolerations. This feature is useful for reserving specific nodes for particular workloads or ensuring that sensitive applications run in isolated environments. So in our city traffic analogy, the scheduler is like a traffic planner, for example, Google Maps, that decides which roads cars should take to reach their destinations. The planner considers various factors such as road capacity, traffic conditions, and any special rules to ensure that traffic flows smoothly and efficiently. Next, we have the Kube-Controller-Manager. The Kube-Controller-Manager is a key component of the Kubernetes control plane, responsible for running controller processes that regulate the state of the cluster. Each controller is a loop that continuously watches the state of the cluster, compares it to the desired state, and takes action to bring the current state closer to the desired state. Technically, the Kube-Controller-Manager manages several important controllers, each with a specific role. The node controller is one of those controllers, and what it does is monitor the health of nodes and take actions if a node goes down. It marks the node as unavailable and triggers the rescheduling of pods to other healthy nodes. Another controller is the replication controller, which ensures that a specific number of pod replicas are running at all times. If the number of replicas falls below the desired count, the replication controller creates new pods to also match the desired state. Also, if there are more replicas than required, it deletes the excess pods. The Kube-Controller-Manager also includes other controllers such as the service account controller, which manages service accounts for pods to access the Kubernetes API, and the namespace controller, which handles the creation and deletion of namespaces. In our city traffic analogy, the Kube-Controller-Manager is like a team of traffic officers who monitor the roads and ensure that traffic flows smoothly. Each officer has a specific role, such as managing the operation of traffic lights, ensuring roads are clear and updating road signals. They work together to maintain order and to ensure that the city's traffic system operates as intended. Before we discuss the worker node components, let's briefly look into Kubectl. Kubectl is the command line tool used to interact with the Kubernetes API server. It provides a powerful interface for managing Kubernetes clusters, enabling users to deploy applications, inspect and manage cluster resources, and view logs. From a technical standpoint, Kubectl sends HTTP requests to the Kubernetes API server, which processes the requests and performs the desired actions. Users can use Kubectl to create, update, and delete various Kubernetes resources such as pods, services, deployments, and namespaces. One of the primary functions of Kubectl is to deploy applications. Users can define the desired state of the applications using YAML or JSON files and then use Kubectl commands to apply these configurations to the cluster. For example, the Kubectl apply command reads the configuration files and sends the necessary requests to the API server to create or update the resources. Kubectl also provides powerful inspection and management capabilities. Users can use commands like kubectl get to list resources, kubectl describe to get detailed information about a resource, and kubectl logs to view the logs of a specific pod. These commands allow users to monitor the state of the applications and troubleshoot issues as they arise. In our city traffic analogy, Kubectl is like the radio or smartphone that traffic officers use to communicate with the control center. It allows them to send and receive information, make updates, and ensure that the traffic system operates smoothly. Now that we've looked into the components that make up the control plane, let's talk about worker nodes. Worker nodes are the backbone of Kubernetes, basically running application containers within pods. These nodes provide the necessary compute resources to execute workloads, ensuring that applications run just as they should. So, let's explore the components of a worker node and their role in the Kubernetes architecture. First, we have the kubelet. The kubelet is the primary agent running on each worker node, responsible for managing the lifecycle of pods. It ensures that the containers within the pods are running as specified and continuously monitors their health. Technically, the kubelet communicates with the API server to receive instructions on which pods to run. When the kubelet gets a request to run a new pod, it pulls the necessary container images from a container registry, creates the containers, and starts them. The kubelet ensures that each container has the required resources such as CPU, memory, and storage as specified in the pod's configuration. The kubelet also performs health checks on running containers. And to achieve this, it uses features such as liveness and readiness probes to determine if a container is functioning correctly and ready to serve traffic. If a container fails a liveness probe, the kubelet restarts it to restore the desired state. And if a container fails the readiness probe, the kubelet temporarily prevents traffic from being routed to it until it recovers. Another key function of the kubelet is to handle pod eviction. If a node becomes overcommitted or maxes out in capacity, the kubelet can evict pods to free up resources and maintain the stability of the node. The kubelet follows predefined eviction policies to determine which pods to evict based on factors such as resource usage, priority, and quality of service. In our city traffic analogy, the kubelet is like a smart traffic light controller at each intersection. It ensures that traffic flows smoothly by managing the timing of lights, monitoring traffic conditions, and making adjustments as needed to keep everything running smoothly. Next, we have the container runtime engine. The container runtime engine is the software responsible for running containers within pods. It provides the necessary infrastructure to manage container lifecycle operations such as pulling container images, creating and starting containers, and handling resource allocation. Technically, the container runtime engine works closely with the kubelet to manage the containers on a worker node. When the kubelet receives a request to run a pod, it communicates with the container runtime to pull the required container images from a container registry. The container runtime engine provides isolation for containers, ensuring that they do not interfere with each other. Containers running on the same node share the same operating system kernel but are isolated in terms of processes, file system, and networking. This isolation ensures that containers can run securely on the same node. The container runtime engine also manages the resource allocation for containers. It ensures that each container has access to the required CPU, memory, and storage resources as specified in its configuration. The container runtime enforces resource limits, ensuring that containers do not exceed the allocated resources and affect the performance of other containers running on the same node. In our city traffic analogy, the container runtime engine is like the engines of the vehicles that drive on the road. It ensures that each vehicle, in this case the containers, operates correctly, has enough fuel, which are resources in our case, and follows the correct routes or networking in terms of Kubernetes. Lastly, we have the kube-proxy. Kube-proxy is a network proxy that runs on each worker node within a Kubernetes cluster. It is responsible for maintaining network rules and facilitating communication between pods, services, and external clients. Kube-proxy ensures that network traffic is routed correctly within the cluster, providing load balancing and ensuring that services are accessible. The kube-proxy is a crucial part of Kubernetes that handles networking, and its main job is to make sure that network traffic gets to the right place. When a new service is created in Kubernetes, kube-proxy sets up the routes and rules needed for network traffic to find its way to the correct ports. This allows clients to access services using stable IP addresses and ports, even though the actual ports providing the services might change over time. One of kube-proxy's important roles is load balancing. When a service is supported by multiple pods, kube-proxy ensures traffic is spread evenly across all pods. This prevents any single pod from getting overwhelmed, much like a traffic system that evenly distributes cars across multiple lanes to avoid jams. Kube-proxy also supports network policies, which are rules that control traffic flows between pods. These policies enforce security and ensure only authorized pods can communicate with each other, similar to restricted areas in a city where only certain vehicles are allowed. Before we wrap up this video, let's discuss managed Kubernetes services. Setting up and managing Kubernetes can be complex, but managed Kubernetes services from cloud providers make it easier. So services like Amazon EKS, Google Cloud GKE, and Azure AKS handle the heavy lifting. They take care of the control plane operations, allowing you to focus on deploying and managing your applications. One of the primary advantages of managed Kubernetes services is the ease of cluster provisioning. Users can quickly create and configure Kubernetes clusters using the cloud provider's console, command line tools, or APIs. The managed service takes care of provisioning the necessary resources, setting up the control plane, and configuring the network and storage infrastructure. And this allows users to get started with Kubernetes quickly and focus on deploying their applications. Managed Kubernetes services also provide automated upgrades and patching for control plane components. This ensures that your cluster is always running the latest and most secure version of Kubernetes without the need for manual intervention. The managed service handles the upgrade process, minimizing downtime and ensuring a smooth transition to the new version. Integrated monitoring and logging are also key benefits of managed Kubernetes services. These services provide built-in tools for monitoring the health and performance of your cluster, including metrics, logs, and alerts, enabling users to gain insights into the resource usage, application performance, and overall health of their cluster. Managed Kubernetes services also offer integration with other cloud services such as managed databases, storage solutions, and serverless computing. This enables users to build and deploy complex applications using a combination of Kubernetes and other cloud-native services. The managed service provides seamless integration and simplifies the management of these services, allowing users to leverage the full power of the cloud. Kubernetes is like a well-organized city in the way it manages and runs containerized applications efficiently, with its control plane components like the API server, etcd, scheduler, and Kube-Controller-Manager overseeing operations, and the worker nodes powered by the Kubelet, container runtime engines, and the kube-proxy running the applications. Kubernetes ensures applications run smoothly and efficiently. Understanding these components and how they work together is key to managing Kubernetes clusters effectively, and I hope this video has given you a good introduction to Kubernetes architecture. Thank you for joining me today. If you have any questions, feel free to leave a comment and I'll definitely respond. Don't forget to like this video, subscribe to my channel, and follow this Kubernetes series closely as we still have a whole lot to cover. I'll see you in the next video. Bye.